This is AI Podcast. I'm Eric, and with me is Maya. Today we're talking about TAPS, Tool Augmented Personalization via Structured Tagging from EMNLP 2025.
And give me the one line first. What's the takeaway?
TAPS adds a small, structured tagging layer to an agent's prompt and only turns it on when the model seems unsure. That combo helps models follow a user's standing preferences and generate cleaner API calls, with fewer mistakes and fewer unnecessary tool invocations.
Nice. Who's behind it?
Ekaterina Taktasheva and Jeff Dalton from the University of Edinburgh.
All right, set the scene for us. What pain point are they tackling?
Think of a task assistant that can call tools. It has to honor your long-term preferences, like prefer American Airlines or default to San Leandro for restaurants. The tricky part is turning a casual request into the right API call while weaving in those preferences. Smaller open-source models often miss arguments, swap fields that sound similar, or hallucinate extra stuff.
Right? And the paper uses that NLSI dataset, the one with natural language standing instructions, to stress test this.
Exactly. It frames the job as parsing a user request plus a user profile into one or more API calls. 2 steps in principle. First, select which preferences matter, then interpret everything into code. This paper zeroes in on the interpretation step.
So what's the core idea behind TAPS?
The authors bet on an intermediate representation. Instead of going straight from free text to code, they tag the user's preferences with lightweight labels that expose the API and its arguments. Picture sticky notes on a profile line that say, API equals get events and city equals New York. Then they ask the model to use that tagged version when it needs extra help.
And the when it needs help part is the clever bit, right?
Yep. They use model uncertainty as a tool detector. The model first tries to produce the API call. If its confidence is low, TAPS triggers the tagging tool, prepends those structured tags to the context, and regenerates the answer. If confidence is fine, it just ships the original output.
How do they tag in practice? Is it a separate model or the same model doing everything?
They try both. One variant uses an external tagger, so a model prepares the tags, and then the base model generates the code. Another variant has the model tag and generate jointly in one go. They also probe what happens if you use a stronger tagger, essentially asking what better tag quality buys you.
And the detector, how does it gauge uncertainty without extra training?
They rely on the model's own logits, the probabilities over tokens. A simple least confidence measure works best in their tests. They set a threshold on validation data and use that to flip between accept the answer or tag and regenerate.
Let's talk experiments. What models and metrics did they use?
Open source instruction tuned Llama and Mistral as the main targets, with GPT-4 as a stronger closed model for comparison and, at times, as the external tagger. They evaluate with exact match of the API program and a slot-wise F1 that checks whether the right arguments got filled.
And results in plain English?
For open source models, tagging helps, and tagging plus detection helps more. The paper reports new state-of-the-art for open source on the NLSI interpretation task, with gains around 16 points in exact match and 17 in F1 compared to prior open source baselines. The detector also saves compute by cutting unnecessary tool calls, roughly a fifth fewer for the open source models and more than half fewer for GPT-4.
That last bit is important. It's not just accuracy, it's deciding when not to use the extra machinery.
Exactly. Always using the tool can actually hurt some strong models. Selective use gets you most of the upside without the overhead.
What kinds of mistakes go down with TAPS?
2 big ones. Hallucinations like inventing a new function or argument that doesn't exist, and semantic substitutions, like mixing up city with area or genre with category. The structured tags act like a scaffold, so the model has less room to drift.
Can you give me a concrete example?
Sure. Imagine a user says, find something not too fancy, and the profile says, if the price is cheap, look for Persian cuisine, and default city is San Leandro. The model needs to output a get restaurants call with city San Leandro, cuisine Persian, price range cheap. Without structure, models sometimes pick the wrong slot names or forget the city. With the tags, those fields are explicitly marked before generation, so the final call stays aligned.
That makes sense. It's like putting labeled baskets on a messy desk so nothing ends up in the wrong place.
Exactly.
Any surprises in the comparisons between the tagging variants?
The joint tagging and generating approach underperforms. It sounds elegant, but in practice it can drop information. The external tagger, even a lightweight one, tends to be more reliable, and better tag quality predictably yields better results, though the detector closes much of the gap by only invoking tags when they help.
Let's be a bit skeptical. Where are the soft spots?
First, everything is evaluated on NLSI. It's a useful benchmark, but it's templated and scored by string matching. Two programs that would behave the same when executed can get different scores on paper. Second, the paper fixes the preference selection step to focus on interpretation. In the real world, selection and interpretation interact, so performance might shift. Third, the uncertainty detector depends on access to token probabilities, which not every API exposes consistently, and the authors themselves show an Oracle detector could do better.
And tag quality itself is a dependency. If the tagger is noisy, you might guide the model in the wrong direction.
Right. They even run a control corruption study showing performance drops as tags get worse. Also, prompts matter. The system relies on in-context learning, so it is sensitive to prompt template and exemplars. The authors do release code and settings, which helps reproducibility, but you'd still want to test robustness.
So how should practitioners think about using this?
If you're building a tool using Agent and you already log user preferences, you can try a lightweight tagger and this uncertainty gate without retraining your model. It's a practical way to reduce silly argument errors and avoid calling heavy tools unnecessarily. Just be mindful of how you measure success and whether you can access the confidences you need.
What would you like to see next?
3 things. 1, execution-based evaluation, where we run the generated calls and score the outcomes. 2, smarter detection, maybe a small learned policy that predicts whether tagging will help on this instance. And 3, richer tags that capture dependencies across multiple preferences and also mark relevant bits of the user's query, not just the profile.
I'd add combining the selection and interpretation pieces into one controller so the system jointly decides what to retrieve, how to tag, and when to call tools, all while keeping latency in check.
Totally. And testing beyond a single dataset, ideally with real user logs and multilingual settings, would round out the picture.
All right, give me the quick takeaway to close.
TAPS shows that a small amount of structure in a simple when-to-use-it rule can meaningfully improve personalized tool use. You don't need to fine-tune a big model. Tag the preferences, check your confidence, call the tool only when it's worth it.
Simple idea, solid gains, fewer wasted calls. I like it.
That's TAPS from EMNLP 2025. For AI Podcasts, I'm Eric.
And I'm Maya. Thanks for listening.